Hi, in this video, we're going to look at another example of shear stress due to the bending. And there's some other names throughout there. They call transverse shear or shear flow. And here I'm just going to call shear formula. So in this situation, quick recap what we covered last time. To figure out this shear, it has its own formula. It's tau is equal to V shear force times Q. Q is a new concept, moment of area. So it's area times some distance. That distance is this area centroid to the neutral axis. Then divided by I neutral axis times B. B is the width of that beam at that point. Okay, and we also know it follows this profile, which means at neutral axis, you reach the maximum of the shear, and at the top and the bottom, the shear is equal to 0. So knowing that, we're going to look at another example. The previous video showed a section, cross-section is a rectangle, but now if it's a circle, how do we find the Q? I want to discuss the moment of area Q only. So Q, remember, has a formula of area times this y, right? Sometimes people put a Q underneath for subscript, but now let's take a look. So if, scenario number 1, if my point of interest is right here, so my point of interest is going to be on neutral axis. So we're going to discover what's Q going to be equal to. Q is going to be area. This area is out from this point of interest. So it's going to be the top of the semicircle. So this area will be pi r squared over 2. And then this y is going to be the semicircle centroid. We know it's right here, right? To this neutral axis. That's going to be my y, or yq. And I believe you already know that's going to be 4 over 3 pi. Because that's the semicircle centroid located, right? So 4 over 3 pi, that's going to be our y. And if we're going to put them together, what's going to be my q? Let's see, pi and pi cancel out, this 1, 2, and 4. So I will get 2r cubed over 3. That's going to be my moment of area for this semicircle. Okay. Now let's look at scenario number 2. If my point of interest is the top, is the top tip. So in that case, this is going to be my point of interest. And what do you think my Q equal to? I mean, still area times y, but what's the area out from point of interest? Nothing, it's just a dot. So it's 0, right? And then you times your y is basically your radius. Then in that situation, you still get 0, and that match up this profile right here, because at the tip your tau is equal to 0 because this q is equal to 0. However, if it's on neutral axis, this q is the greatest. Therefore, we get our maximum shear at neutral axis if it's located at the neutral axis. Okay, so that's for this problem. So imagine we can do a quick example. So if I'm going to give an example, let's see, given. And for this problem, it's a low-hanging fruit because they didn't give you the external loading. And then for you to find out the maximum shear, they actually give you the maximum shear. They said maximum shear for this problem is 125 pounds for some kind of loading condition. And this cross-section is a circular shape. And they want you to find what's going to be the maximum shear. Okay, so I want you to think about it. You can pause to think about it. So, okay, so we're back. So tau max is going to be this V max times this Q max over your I neutral axis times the B, the width at that point. Okay, so when do you get maximum? The maximum occurs at neutral axis. And so in that situation, no matter what, your Vmax is stay the same, no matter where your point of interest is, because Vmax is the location on the beam, right? In terms of x equal to, for example, x equal to 3 meter, that's when you get maximum shear. But here Q is going to be when you cut at this maximum place, and then you have this cross section. This Q max happen the most, reaches the highest when it's at the neutral axis. And this value, you already know it's this 2r cubed over 3. So you don't need to redo it. You can just use that. Same thing for the rectangle you did earlier in the previous video. If you go back, pause the video, go back to look at it, that should have a formula. That would be 1/8 BH squared. Okay, that's gonna be for your cube max. So here for the circle, it's gonna be 2r cubed over 3, and then the neutral axis moment of inertia for circle, we know that is going to be 4 pi over 4th, right? 4 pi r 4th. Okay, and then what's going to be the B? What's the width at this point of interest? This is our point of interest. It's at the neutral axis. The width of it will be this, right? The width of the cross section. That will be the diameter. That's going to be your 2r. So here you can go ahead and solve this problem, and imagine here you are using Newton meter for the, Newton for the shear. Let's look at the unit. So Newton for the shear, Q, what do you think the unit for the Q moment of area would be? It's area times distance, so it's going to be meter cube. And I, it's moment of inertia, it's meter to the 4th. And B, it's again the length unit, so that's meter. So eventually you will get Newton meter squared. That's your Pascal. So in this situation, if everything is given in pound, and yeah, okay. So if this is given in pound, and this, if I give you R here, is in 2 inches, then our number we got here is going to be pound per square inch for our unit. So I will leave you to finish this problem if you are curious to finding the answer for this. So that's going to be the maximum shear for this one. Okay, that's the shear due to bending. All right, I'll see you at the next one.